groups, and we will do so with some intuitive ideas, because computing them formally is a very difficult task, and it will require some advanced machinery of group theory as well. So maybe we'll discuss that later, but for now let us look at some examples that are pretty simple. So we start the section, let's say, computation of fundamental groups. And let's say this is your example 1. Let's say I have an n polygon like this. Okay, and this is homomorphic to a disk as well, and it is inside field. We want to compute the fundamental group of this polygon. Okay, now at first what you do is that you take a base point, let's say any base point x0. Now around this base point you can draw a loop like this one, right? You can draw another loop. You can draw another loop like this, and another. Obviously the loop doesn't go outside the space, just the drawing is pretty bad, or this. But no matter which loop you take, you can see that you can shrunk all these loops into the trivial loop x0, right? Because you can draw a loop at base point at x0, and all these loops you want to see how much you can deform them. Is that all these loops, they are equivalent to each other and they form an equivalence class, right? But all the elements of that equivalence class is nothing but the trivial loop itself, because when you are doing a deformation retract, or you are shrinking the space, so to say, and under that continuous family of continuous deformation, all the points, let's say you take a base point and all of it's getting shrunk to this x0. So there is only one element in that equivalence class, and that is just the trivial loop itself. So there is only one element, which is just the trivial loop. So your fundamental group for this n polygon, pi1 of n polygon, let's say at on some base point, is just nothing but this loop, let's say, or if you want to write it as a class as well, you can write that, where alpha 0 denotes the trivial loop. And you saw that just this intuitive argument is good enough to extract this information out. And now if you use the idea of homeomorphism, that my n polygon is actually homeomorphic to the disk, like this is my n polygon, right? My inside is field, this is homeomorphic to a disk. You can also say that this pi1 of d squared with some base point x0 is just this alpha 0, the trivial loop, or the trivial group, and some people even write it as a 1. Okay, but we won't do that, rather we'll just keep alpha 0. Now for the second example, and this is an interesting one, we want to compute the fundamental group of the circle, okay, with some base point. This is the thing we want to see. Again, we draw. Let me draw. Okay, this is a good circle, And let's say this is the base point x0, and let's call this 0 equals to 1. What I mean by that is that you go from x0, start and round up the circle. If I call this point 0, that means what I'm essentially doing by writing 0 equals to 1 is that you can take some interval, right? And that interval, let's say there is some parameter t. T takes values from this interval, and for different values of t you get different points on the circle's arc or the perimeter, whatever you want to say. And when you make a complete loop, you are back to where you started. So that's why I wrote it as a 0 equals to 1. Oh no, I need to remove the circle again. Okay, so let's try to draw that again. There it is. So let's say this is the base point x0, where we have a 0 and 1, the periodicity. Okay, now again we'll do this the intuitive way. We have our base point over here. One thing for sure is that all the trivial loops alpha 0, that is the trivial loops or the constant loops, are here. You can take any point and that is a constant loop, right? Now let's define a loop that goes like this. Please note that I'm not going outside the space, that is I'm not going outside the circle. Just for the drawing purposes I'm drawing it like this. What you should imagine is that you are on the top of the perimeter of the circle and you are going around like this. So let's say this red line goes around the circle like this. This is a loop, right? And let's say I call this loop as alpha 1 with t such that alpha t is equals to t, right? And this makes sense. When t is equals to 0, alpha t is also 0. When t equals to 1, alpha t is also equals to 1. But at this point 0 and 1 are equal. That means they're the same point, so it makes a loop like this. In fact, instead, this is just one element that I can have within defining this alpha t with t. What I can do in the meantime is that I can wiggle it a bit, right? That is also an element of the loop that I'm talking about right now, because I can continuously deform it to get back to the same place I was. So there is this equivalence class, and all the elements can be found like wiggling like this in each and every point, right? So now that's out of the way. This is one thing, this red loop denoted by alpha 1t. Now someone else said, okay, let me say I want to define a loop like this. What does this alpha 2t equals to 2t means? Well, this means that your t is running from 0 to 1, right? So when t is 0, alpha 2 is 0, right? And let's say this is the loop. At first I'll draw the loop and then I'll explain what I'm actually doing. So this is my alpha 2. When t is 0, this is 0. That means it's at this point within the base point. Okay? But t runs from 0 to 1. So when t equals to half, alpha 2 is equals to 1. But 0 and 1, we are identifying them to be the same, right? It's like taking the interval 0, 1 and we're gluing it together to make the circle. So when t equals to half, you have already traversed the loop or traversed the circle one time. Okay, But t again, from 1/2 it has to go to 1 because t has to run from 0 to 1. So again, when t equals to 1, you have something called a 2, but you don't have 2 over here, so you have to mod it by 2. What this means is that when you are here, you are done rotating around the circle, so to say, or you have returned to the base point once, but from that base point you run again and make another circle. So what happens is that even though this looks like a circle or one loop, instead this is something like this. That means you have crossed the circle twice. So instead of a circle, drawing a circle like this, think of it as beside the circle you have a rubber cylinder made out of rubber sheet. So this alpha 2t means that you are wrapping the circle with that rubber cylinder 2 times. And similarly, I think you can get the pattern now, is that you can define alpha 3t as 3t, alpha 4t as 4t, similarly alpha nt as nt, right? And note the fact that I'm using this anti-clockwise direction as a positive thing, so one can now come on and say that, oh, I want to define an alpha minus 1 of t as minus t, like this. I can define an alpha 2 of t minus 2 of t as minus 2 of t. So alpha minus n, or say m of t as minus mt, right? And these are just individual loops, and all of these loops will have their equivalence classes as well. And now, and if you ask how, well, just like we said before, you can wiggle it a bit. We can wiggle it a bit there, so you can generate a set of loops that are equivalent to each other because they're related to each other by continuous deformation. So now that all that's out of the hand, it might seem a bit overwhelming at first, but there's a beautiful thing that you can realize is that by defining things like this, let's say you have some alpha n of t as nt and alpha m of t as mt. Again, these are just individual loops, right? So if you take their product, alpha n of t, alpha m of t is nothing but the m plus n of t. How? Well, let me again show you by the diagram. Again, this is our circle. Now let's say I have this multiplication, alpha 1 with alpha 2. So what I'm saying is that you should get, oops, sorry, it shouldn't be over here, m plus, it should be, instead I should write it like this, m plus n of t, which eventually means m plus n, but yeah, I should write it like that because that's the appropriate way to write it. So take alpha 1 and alpha 2. So this is just a one loop, and this is the two loop thing. You are circling the circle twice. You are rotating around the circle twice. Okay? This should give you alpha 3. That's my claim. And the way to see it is that, let's say this is the first loop. You go around once, right? And then from there, after you have already done the first rotation, then you rotate 2 more times, and this is nothing but the third one, because the third one actually tells you to rotate around the circle thrice, like this. Even though this is not the proper diagram, because the one time so these indices actually count how many times you go around the circle, and they add up, because once that you have done this first rotation, it tells you, this alpha 2 tells you, oh, rotate 2 more times. So you rotate 2 more times. So how many times you are rotating in total? You're rotating 3 times in total. Similarly, alpha 1, alpha, let's say minus 2 would give you alpha minus 1. Why? You are rotating in the anti-clockwise direction once, but then you are rotating in the clockwise direction twice, right? So eventually you are rotating in the clockwise direction once, because you can think of it as the anti-clockwise rotation is getting cancelled by the first clockwise rotation, and then there is another rotation in the clockwise direction. So in general, you have for any two loops the product as alpha m plus n. And since our earlier discussion showed us that if we have the products of loops, then that product naturally defines the product between their equivalence classes as well. So with that in our hand, we finally denote the product of two equivalence classes as alpha m plus n. And this is isomorphic to the group of integers, because you can think of it like this. When you talk about the additive group of integers, you have what? Let's say a and b, two elements belongs to z. You have this a plus b operation, right? And here you have all the things. What you're seeing is that they are getting added, and this is the these are the things that gives me the information about how many times I'm going and which way I'm going. So eventually they are the things that are giving us information about those loops, and from those loops we can get those equivalence classes, and from those classes we have our fundamental group. And this additive structure is the same as the group of integers. So finally we say that the fundamental group of a circle is isomorphic to the group of integers. Okay, these two examples will do for now, because computing fundamental groups for other complicated surfaces is very complicated. What we will do is that we will present a powerful theorem. Powerful theorem to compute fundamental groups of complicated spaces by using the results from simpler spaces. And now we present a theorem that we talked about a few seconds earlier. So this is a theorem. Again, we will accept this without a proof.